At the end of the class, what I'd like for everybody to have is the ability to know which analysis to conduct, know how to conduct it in one of the stats programs or even by hand if you'd like, and how to report those results in APA style. I think that that's key to success in this course. And so this is the first chapter where we really get into one of the statistical analyses that we're going to conduct, which is the correlational analysis. We are going to look to see if two variables are related. What we have here are greeting cards sent and received by 5 different friends, Andrea, Mike, etc. So Andrea sent 5 and she received 10 from her friends. These are both what they're called dependent variables. They're not independent variables because we're not manipulating anything. So this is going to be an observational study. And you know this, you've heard correlations, not causation, probably a million times in your life. These are not in control of the researcher. We're just reporting what we see. Okay, so a positive correlation or positive relationship, basically as one score goes up, the other score goes up as well. So high with high, low with low. A negative relationships means that as one goes up, the other one is going down. So high with low or vice versa. In the next chapter, we'll kind of move from using correlations and go into regressions. And what the idea there is that we can use it as that relationship is almost a predictive power. So like the years that someone smoked, you might be able to make a prediction about how old they would be when they get cancer, like for a life insurance premium. And so companies that do work like that will use variables that are related to make predictions to do some type of, in this case, like a financial thing. Okay, so just if you think through it, indicate whether the following statements suggest a positive or negative relationship. So more densely populated areas have higher crime rates. So think about that. Populations going up, crime rates going up. It's a positive relationship. Obviously, both those things are, well, at least the higher crime rates is negative, but it's actually a positive correlation, even though we're talking about something negative like crime rates. School children who often watch TV perform more poorly on academic achievement tests. So TV viewing goes up, scores go down. This is going to be a negative relationship. And we can see these two variables together in what's called a scatter plot. It's a graph that contains a cluster of dots that represents all pairs of scores. So for example, if we went back to that table, we would see Mike sent 7 and he received 12. So there's 7, there's 12. So that's Mike's dot on this scatter plot. And these are the other 4 friends. You can see a scatter plot and you can kind of make a guess on what's going on with that data. So for example, with this one, it's height and weight. And so as weight goes up, or height goes up, weight goes up. And so you can see it there, that there's a positive relationship. That slope, you can see it there. Life expectancy and years of heavy smoking, you can see if that's a negative relationship, and you can see that line there if you think about it. And then if it's just kind of scattershot, it's just everywhere, like life expectancy and height, there's not a relationship between those, so there's little or no relationship there. You can also, by looking at a scatter plot, you can make a guess as to how strong that relationship is. So for example, we got foster child's IQ and foster parent's IQ. And there is a relationship here. It's the correlation that Pearson's R, we see here is a 0.27. 0.27 is not super high, but there is a relationship here between foster child's IQ and foster parent's IQ, which makes sense. So they're not related genetically, but they are in that same environment, and the foster parent is providing the schooling or whatever. And so there's going to be a relationship between that kid's IQ and the foster parent's IQ. If we look at the next one, a child's IQ and the parent's IQ, biological parent, we get an R of 0.50. I'll come back to this in a little bit, but the correlations go from -1 to +1. So 0.50, pretty good correlation. And this would make sense. So they are related genetically, they are related biologically, and then also, they share that same environment. If you look at this one and you look at this one, the dots are closer together. It's more concentrated, meaning it is going to be a stronger relationship. As we see on this last one, they're even closer together. Twins IQs, 0.75. Very strong relationship there. So if you look at this one, you could see that they're more concentrated, meaning that R, that Pearson's correlation that we'll talk about a little bit more later, is going to be bigger. Everything I was just talking about is what's called a linear relationship. And so it's described best with a straight line. If we go back here and look, you can see a line kind of like through there, a line through there. In theory, you could have a curvilinear relationship where it kind of goes like this. I might have a picture on the next. Yeah. What is this? Physical strength and age. So your physical strength as you age goes up, up, up until about 40. And then for a lot of people, it starts to decline like this. So it goes up and comes back down, curvilinear like that. There are other examples like the idea of anxiety and performance. You want to have a little bit of anxiety, but you don't want too much anxiety, because if you do, performance would go down. But if you don't have any anxiety, performance will be low because you don't care. Okay, so a correlation coefficient, it is a number between -1 and +1 that describes that relationship between those variables, like that 0.50 that we saw, the 0.75. Usually, when we're talking about quantitative variables, which is what we're going to be using mostly, we're going to use the Pearson correlation, or R. And it is a number between -1.00 to +1.00 that describes that linear relationship between those two quantitative variables. Cohen's conventions for correlations, these are, kind of subjective, but there are some things in stats that are. This is just kind of the conventions that we go with. If you get an R of 0.10, we would say it's a weak correlation. Moderate correlation would be 0.30, and a strong relationship would be 0.50. And so, yeah, it's based on the number, not if it's positive or negative. So, for example, a negative 0.90 is a stronger relationship than either negative 0.70, but also stronger than 0.70. So it's not about the negative and the positive, it's about the number. So negative 0.9 is a stronger relationship than a positive 0.2. An R of 0.70 for height and weight for college students. If you had that correlation, it's like, how could you describe that in words to someone else? And one way you could say that basically is that taller students tend to weigh more. Makes perfect sense. An R of -0.42 for time spent taking an exam and their exam score. How you could say that in words is students who take less time on the test tend to make higher scores because they know the material, so they're able to go through it really quick. And so there are some examples of this in the homework where you're supposed to supply a verbal description for the correlation. So an example, an R of -0.84 between mileage and automobile resale value. How would you say that in words? How I would say it would be something like, as your mileage goes up, your resale value goes down. Makes perfect sense. So, if you have a car with 100,000 miles, it's not going to be as valuable as a car with 300,000 miles on it. Okay, there's a couple different ways to do the correlations like we did with the standard deviations. This is one way of doing it by hand. We're going to take each variable, each x variable, minus the mean, kind of like standard deviation. Same thing with the y, and we're going to take those times each other and add those up. We're going to divide that by a similar formula, each score minus its mean squared. We'll sum those up for both x and y, take those times each other. This is really close to standard deviation in that we're taking each score away from the mean, and because it's going to equal 0, we'll square them to get rid of those negative signs, and then we'll square root it. Okay, so we need to get the ends and the means. In for this one, 3. In for this one, 3. The mean is, 6 divided by 3 is 2. And over here, 8, 9 divided by 3 is 3. Then we will we're going to do this part of the formula here first, the bottom part. So we're going to take each number minus its mean, and our mean is here is 2. -1, 0, and 1. Over here, -3, -3, -3, go to -2, a 0, and a 2. And remember, on each side here, -1 and 1, if we just add those up, again, we're going to get 0. Over here, -2 plus 2, 0. It'll always equal 0 when you take those deviations from the mean. And it's also related to that degrees of freedom. So this number, one of the numbers here, is not free to vary. We know what it is mathematically. In any case, how we'll fix that is we will square everything. So we get 1, a 0, and a 1. Over here, we get a 4, a 0, and a 4. So we add those up, and just like with the standard deviation, it is called the sum of squares. So you'll see it a lot as SS. The SS for the first data set, the first variable is 2. and the SS. Sum of squares for the second variable is an 8. And again, a different color. That is this bottom part of the formula. So this part right here is a 2. This part right here is an 8. Okay, on the next part of the formula, the top part, we actually already have a lot of this. So each variable minus the mean, we already have that right here. That's for the x variable. For the y variable, we have it right here. And so what we're going to do is take those times each other and add those up. So they're in parentheses, so we'll multiply them by each other, and then we'll add those multiplications up. So -1 times -2 is 2. I might have to change my color here. Is it 2? 0 times 0 is 0. So I'm looking at this number here and this number here. So 1 times a 2 is a 2. So what we're going to get for this part here, the top part of the formula, is a 4. So we're pretty close. Now we have a 2 and an 8 on the bottom. We need to take those times each other, so we will get a 16. But if you remember, everything was squared, so we need to square root it. So we'll take the square root of 16, and we're going to get a 4. So now we have a 4 on bottom, 4 on top. 4 divided by 4 is 1. So we have a 1.00, meaning we have essentially a perfect correlation with these numbers, 1, 2, and 3, and a 1, 3, and 5. And you can kind of see it. It's as one goes up 1, the other one's going up 2. If my handwriting wasn't up to snuff, I do actually have this all those calculations here in the PowerPoint, taking each number minus the mean, getting our sum of squares. Sum of squares 2 and 8. Then yes, the -1 times the -2 to get to 2. We get the sum. That's that top part. That's the 4. 4 divided by 4. Yeah, perfect correlation. At least in one textbook, it uses this formula, and we could use it as well. I like the formula that I just did because it's intuitive, but there's 2 problems you can run into. One, if your mean is a decimal point, the calculations could get a little bit trickier, and you could be more likely to make a mistake. And then also, if it's an approximate number, that if you have to round it, you will have rounding errors. So your correlation will not be it won't be as precise if you do it using the first method. This method's more precise. The first method is more intuitive, maybe quicker, depending on how you feel about it. What we're looking at here is the sum of squares for x and sum of squares for y, and then what they call the pooled together with x and y. So here's what that looks like. If you want to get sum of squares of x using this formula, you would take each variable minus the mean, you'd square it, you'd sum those up. Yes, the sum of products is the way to word that, the SPXY, and so you take each one times itself, kind of like in the top part of the other formula that we used. And this is how you could put it all together if you wanted to do it this way. So you would line out your variables. The first thing you do is get your N of 5. This is for the cards sent and received example. So we have our cards sent, which is the x variable, cards received, which is the y variable, and then this goes through each step. So the first step, you get your N. The second step, you sum all of your x variables. So that's sum of x, so 13 plus 9, etc. is 35. You sum up all of your y variables, 14, 18, and you get 60. In step 4, we will take x times y. So 13 times 14, 182. You go through each one of those. Step 5, you're going to add up. I know it's a lot of stuff. You would add up all of those products of x and y to get 484. Step 6, you're going to square all of your x data points. So 13 times 13 is 169. You would also do that for y. So 14 times 14 is 196. You're also going to sum all of those up. So the sum of all of the x squared, 325. The sum of all the y squared is 800. Now that we have all those numbers, we can plug it into that formula, this formula here. So our sum of squares for x, if you plug it through that formula, is 80. The sum of squares for y is 80. And then the sum of the products of the two, we get 64. If we go through that formula, now we're pretty similar to the formula that we used, the 60 divided by the square root of 80 times 80, and then you get a correlation of 0.80, meaning that for cards sent and cards received, R, the Pearson's R for that, is 0.80, which is a really strong relationship. You might think to yourself which formula you like to use. Again, the one that I do, the one that I like to use, just makes intuitive sense to me. It doesn't seem as difficult, but yeah, you do lose some precision doing that. And for some people, they like things lined out like this. They like a very strict formula and you just plug the stuff in. In any case, you're probably never going to do a correlation by hand. You can do one. I have an extra credit assignment where you can do one if you would like to do one, but I'm not going to force you to do this kind of stuff by hand because some people are just like, no, and you're never actually going to do this. I think it's helpful to do it by hand. It might show you how things kind of work. But in any case, we are going to use some stats programs to get those answers. Okay, so here we have SPSS. This data, the save file, is in the modules. And these are the cards sent, cards received. Should be exactly the same. And it's not too difficult. I do have it listed here. Analyze, correlate, bivariate, move those two variables over, and then click OK. Correlate right there, bivariate, two variables. We're going to sent and received. You can put them over one at a time like that, or and what I'll do frequently is I'll press Control and you can get both of them at the same time. Move those over. We got Pearson's, two-tail, flag significant correlations. That all sounds great. Sure, let's see the means. If you click Options, you can see the means and standard deviations. Click Continue and click OK. And here's our output. So yeah, it's cards sent, the mean 7, cards received 12, there's your standard deviations, our ends, and then we have our correlation. So here it's sent, and it's comparing it to received here. Sent to sent is going to be 1, and received to received is going to be 1 because it's the same variable. Sent to received, though, we have our sent to receive is a 0.800, just like what we got when we did it by hand. Something we did not do by hand was to discuss if it was significant or not, and we'll discuss what significance means much more in depth in chapters, I think it's 9 and 10. But for right now, and you've probably heard this before, significant value, generally speaking, in psychology research, psychological research, is a p less than 0.05. And this p, the significance, two-tail, is 0.10. So this 0.10 is above a 0.05. What that means is not a significant finding. And you might think to yourself, well, how can that be? That R is so big and such a strong correlation, how can it not be significant? And the reason for that is our sample size. It's very small. If we just double up the sample size and we have this R 0.80, we do get a significant finding. So yeah, that's what the 0.80, you can see this in the PowerPoint. And yes, level of significance is from chapter 10, and we will discuss this much more later on. So if this is a little bit confusing, don't worry, we'll talk more about it later on. It's the degree how rare the outcome is. And when we get into hypothesis testing, we'll talk about the null hypothesis and the alternative hypothesis. The null hypothesis is essentially there's nothing going on here, there's no relationship. And the alternative hypothesis is that there's a relationship and that there's a relationship between cards sent and cards received. SPSS, it tells you what the, if it's significant or not. If you wanted to know how to do it by hand, this is how it works. You take your R times the square root of n minus 2, and we'll talk a little bit about what that means here in a second. It's degrees of freedom. Divided by 1 minus your R squared. You would get that number, and then you would go and compare it to our table. In that example, we have 5 data points on each side. So for variable y, there's 5, and for variable x, there is 5. There's 5 pairs there. However, if you remember when I was doing those calculations, the one number on each side is not free to vary because of how the math works behind it. Every time I would add up to 0, and so we know what that other number is. So if you're doing a correlation, there's going to be 2 numbers that are not free to vary, one on the x and one on the y. When we look at our degree, this here, df, degrees of freedom, if you have an n of 5 for correlation, your degrees of freedom, n minus 2. So 5 minus 3, and we would get degrees of freedom of 3 right there. And so we would need to hit a critical value of 3.182 to say that this is a significant finding. Well, if we plug that information into this, which I can probably do, so let's see here. Okay, so we could try to do this. Let's see. Our correlation was a 0.80. Square root n minus 2 divided by 1 minus r squared. 0.80 squared, 0.64. 1 minus that would be a 0.36. N minus 2, again we had 5, and so it's going to be 3. 3 divided by 0.36 gives us an 8.33. Oh, and then the 0.833, we need to do square root of that, which gives a 2.89. So 2.89. And then the final thing is we need to take it times our r again, right up here, which is 0.80. So that number times 0.80. We're going to get 2.31-ish. 2.31. So 2.31, we needed to get, right there, a 3.182. 2.3, obviously, less than 3.182. That is our critical value. To say something's significant, you need to exceed that critical t value. In this case, we didn't, and that's why it's not significant. But again, if we add more, if we make the sample size bigger, it will. So right here we have n minus 2 is 3, but if we just double up and take, we have 5, if we get 10, or this number would turn into an 8, and we would definitely get that critical t value, especially because if you'll notice, the critical t value gets smaller the more participants that you have. And so if we take this up to an 8, we would only need a critical t value of 2.31-ish. All right, well, while we're here, let's see. Oh, here's the one I did by hand, 1, 2, 3, 1, 3, 5. Let's do that one real quick. Analyze, correlate, bivariate. I would reset it, move over 1 and 2. Click OK. There we go, just like I said, perfect correlation, 0.100. And let's just do another one just so you can see what it looks like. This is from the field text, adverts, the number of adverts that someone sees, and then the number of packets that they use. This like a sugary, like equal or whatever. So the more adverts you see, maybe the more packets that you would end up using. So let's see, analyze, correlate, bivariate. Let's reset that. Adverts, packets. Click OK. Oof, yeah, so it is 0.871, but it's not quite significant. Again, for something to be significant, it has to be less than, generally speaking, in psychological research, you need your P, that's what that's called, the significance, less than 0.05. So 0.054, it's not. Even if you round that, and so if you were to say P equals 0.05, it's not really right, because again, we're trying to hit that critical t value, and if you're rounding it like that, so like if it's 2.306, your calculation would probably be like a 2.04, so it's not actually meeting or exceeding that critical t value. So yeah, it's not going to be significant if it's a 0.054. But again, all that's the hypothesis testing that we'll talk about much more in chapter 10. So if that part doesn't quite make sense, just keep in mind, we'll talk more about it later on. This is what it looks like. This is what that one looks like. It's in the PowerPoint if you'd like to look at it. And additionally, so again, I talked about you need to know the proper analysis to conduct, how to conduct it in some type of a software, and how to report it in APA style. And this is how you would do that for a correlation. The number of cards sent and the number of cards received was not significant or non-significant, comma, your R, your degrees of freedom, and -2 equals 0.80, comma, P greater than 0.05. So if the P is greater than 0.05, non-significant, P less than 0.05, significant or a rare, super rare finding. Same thing as this one. There was not a significant relationship between the packets of sweets purchased and the adverts watched. So technically, yeah, 0.050001 is not significant or non-significant. The sample size is too small though, so we should have a bigger sample size. But that being said, you shouldn't just keep increasing your sample size chasing significance. Before you do a study, you want to do what's called a power analysis that tells you how many participants you need. And if it says you need 80 participants, run your 80 and be done with it. Don't You shouldn't be like, well, we're really close at 80. What happens if we do 90 or 100 or 500? It's like, it's technically not how you should do it. You could, some people will say this, it's up to you. If it doesn't quite get to that 0.05, you could say that there's a trend towards a significant relationship. You could also say that it is marginally significant. So if you have like a p 0.06, you might say there's a trend towards significance, like it's moving that way. One of my professors when I was in grad school though said that, it could also be moving away from. In any case, it could be, you could also say it's marginally significant. And there will be studies that are published with a p of 0.06, 0.07, because yeah, it's close. And so, yeah, let's see it. But yes, technically do a power analysis, run that many, and then report it as not significant, non-significant, trend towards significance, or marginally significant if you get like a 0.06 or 7. Okay. I think that's it. Hopefully some of that made sense. If it doesn't all make sense, it's okay. We'll come back and revisit some of those. Also, I can do it in R real quick as well. I do not remember where I got this data from off the top of I think I created it myself. I did for a test or something. In any case, let's say we wanted to look at the correlation between income and happiness. So we're going to look at income and happiness. I already have this pulled up. If I needed to pull it up, what I would do is, this was an Excel file that I have on my desktop. And so I would put that read CVS, and then I would point RStudio to where my file is at. Click enter. You'll see it pulled those up. There's all my data right there. And then also what you can do is check to make sure it's actually there. If you do head R examples. And so yes, it is there. Just to double check it to make sure. Sometimes you'll pull it up and it'll act kind of weird, and what you'll need to do is actually name this. I'll just do it real quick. So I've got it pulled up. I can call this, what I have this called is R examples. What you can do is R examples, that's the thing I'm naming, that arrow pointed towards it, and then pull up that exact same file. And then check it again, just make sure. Nothing is more frustrating than when they're not actually there, but they are there. Okay, so to run a correlation in R, you're going to do cor.test. We're going to talk about R variables, which is the like our data file, which is R examples. And then we're going to pull up the variables that we want. And in this example, I want to do income and happiness. So what you do is do $, and yeah, they'll come up. And so I want income, and then comma. R examples, your second variable, $, and happiness. cor.test, and then you're pulling up your two variables from that R examples, income and happiness. Click enter. What this is telling us, so this is giving us our degrees of freedom, like with SPSS. This is giving us a p-value as well, 0.02. So yay, we got a significant finding here. It gives us the t-value as well. Gives us the 95% confidence intervals. We'll talk about those in a couple chapters, but this is what we're looking for right here. There is our R, 0.6485. So yes, we have a significant relationship. R 0.65 is what I'd put. R, parentheses, your degrees of freedom, which is 10. So R 10 equals 0.65, comma, P. You could put less than 0.05. That's probably what I would do. But if you are, if you want to be more precise, you could put P equals 0.02. And that would work too. All right. Hopefully that makes sense. If it doesn't, please come ask me or one of the TAs. Thank you very much for listening.